Hey guys, day 9. We're looking at a quiz tomorrow over the first 9 days worth of materials, and so let's make sure we're ready for that. For today we have 2 topics to talk about. We're going to talk about what are called rational powers, which are when your powers are written as a fraction, and we're going to talk about how to rationalize a fraction that contains a radical. 2 very different topics. Both should be pretty straightforward. We have a very short homework assignment for tonight in preparation for our quiz tomorrow. Don't forget, the quiz tomorrow will encompass material from all 9 days. It'll be, I'm looking at a total of about 10 questions, and it'll be due on Friday at noon, just like everything else. If that's a problem, please let me know. I'll be happy to work around that. Let's go ahead and take a look at today's material. Okay, so for today, let's talk about our 2 major topics. We have rational roots. Rational exponents would be a better way to put it. And we're going to have rationalizing a denominator. So let's talk about the first one, rationalizing exponents. So it is important to note that if you ever see a radical, so for example the square root of 24, I'm not going to bother simplifying, but I do want to make note that there is another way to write this. All square roots can be written as a fractional power. In this case, every square root is actually a 1/2 power, meaning you have the square root of n, it is equal to n to the 1/2 power. And note, there is a pattern to this. If you have the cube root of n, it's n to the 1/3 power. If you have the 4th root of n, it is n to the 1/4 power. And as you can imagine, this trend continues. Now, the reason why it's a 1/4 power, or a 1/3 power, or a 1/2 power is because the power on the n is a 1, the power on the radical is a 2. To write this root, we do the power of the number 1 divided by the power of the root 2. The power of the number 1 divided by the power of the root 3. The power of the number 1 divided by the power of the root 4, so 1/4. So if you ever come across the nth root of the mth power, it just means the top number is the power with the variable, or with the number. The bottom number is the power of the root. And as you might imagine, if we cancel a square root with a square, you cancel a cube root with a cube. A 4th root with what's called a quartic, or 4th power. And if you are unsure, it works for any matching root. And so this trend is always true. These are referred to as rationals, because you can write any of these radicals as a rational power. Notice the fraction we're talking about here is in the power, not in the problem. Big difference here, okay? So let's look at a couple of these. First, let's make sure we understand the basic concept. If, for example, I have the 5th root of 32. So what this means is, if I want to cancel this 5th root, I need a 5th power. So one thing that I can do the 5th root, and I can take that 32 and write it as the factor tree of 32, which would be 2's. And then we could combine those together into a power. So we have the 5th root of 2 to the 5th power. Since the root and the power match, they end up canceling, meaning the 5th root of 32 is, of course, 2. Now, the 5th root of, let's say, 20, right? The 5th root of 20, we could rewrite as the 5th root of 4 times 5, or we could rewrite it as the 5th root of 2 times 2 times 5. So we could rewrite that as the 5th root of 2 squared times 5. Since none of these match powers, like, I can't get the 5 to cancel, right? The 5 cannot cancel with the 2 because they don't match powers. We need them to match to cancel. and the power on this 5 is a 1, and that's not going to match the 5, and so those aren't going to cancel either. And so in this case, this would represent a function which the answer would just be what you started with. The fifth root of 20 is just the fifth root of 20. It doesn't simplify any farther. Because remember, the definition of simplify is the smallest possible radical. And 20 is the smallest number that can go into the root of 5. If I was to look at something like, say, the fourth root of 48. Well, again, I could start the same way I have before by rewriting 48 using a factor tree. 48 breaks down into 4 and 12. 12 breaks down into 2 and 2. 12 breaks down into 4 and 3. 4 breaks down into 2 and 2. And so I can see here that I can combine my 2's together to get 2 to the 4th power times 3. And now I could use my same properties that I did before, allow me to take this radical and split it. And just like before, when I split it, the root's not going to change. So they're both going to be fourth roots. And now the fourth root and the fourth root can cancel, leaving just a 2. And there's nothing to cancel the root with the 3, so it would be the fourth root of 3. And so the fourth root of 48 would be 2 times the fourth root of 3. These are equivalent statements. Now, if you're using a calculator, many times you'll see a fractional button that shows something like x to the a over b. If not, you might see the housetop button. Many calculators contain the square root, and even a few contain the cube root, but many don't contain anything past that. And so you can use the caret, as it's called, to take a number and type it as a fraction. So for example, if I wanted to use this on my TI calculator, I would type in 48 caret 1 over 4. And make sure to put the 1 over 4 in parentheses so it knows that it's one thing to that power. And so this would tell me how to do the fourth root of 48. Well, those are, great for talking about, but you need to know how to do both parts of this, which is whenever you're dealing with a function with powers inside and out. So let's take a look at another one. What if I offered something like the cube root of 343 squared? First of all, this is not the only way to write that statement. It should be noted, another way to write this would be 343 to the 2/3 power. These two are equivalent statements. You have the cube root, which is why the 3 is on the bottom. You have the square on the inside, which is why it's a 2 on top. If there's no number on the inside, it's a 1 on top. And so these two are equivalent. This one, we could, square 343 and try to get this to work out, but instead, I'm going to choose to rewrite. This is the cube root of 343 times 343. Because remember, that's the definition of a square. So, at this point, I could break down 343 and 343. It turns out 343 is 7 times 7 times 7. And 343 is 7 times 7 times 7. Which means this is actually the cube root of 7 to the 6th power. Now, I could break it apart using the fractional rules from last time, where I tried to, split it here and do, the cube root of 7 cubed times the cube root of 7 cubed, and that'll work. Or I could use the rules of today, which allows me to take this statement, which is the cube root of 7 to the 6th, rewrite it in fractional power, so 7 to the 6 over 3. Remember, power on the inside goes on top, power on the outside goes on bottom, and you can clearly see that 6 divided by 3 is a simple equation. 6 divided by 3 is 2, and 7 squared would be 49. I'll get the same result if I had gone the other way, because the cube root would cancel, leaving just a 7. The cube root would cancel, leaving a 7. 7 times 7 is, of course, 7 squared, which is the same as 49. And so no matter which way we go, we're going to get the same results. But this gives me just another option, another tool to use. It means that I can take these functions and do them in a very different way and still get the same result. Take a look at this one. So something like 9 to the 5/2 power. Okay? Well, 9 to the 5/2 power. One thing we could do is we could perform a rewrite. Because if I divide 5 divided by 2, I end up with a decimal, and that's not good. Decimal powers are not in our vocabulary that we've talked about so far. We have rational powers, and we have radicals. We do not have decimals. So I cannot do, 9 to the 2.5. That's not allowed. Okay? Yes, I know 5 divided by 2 is 2.5, but we can't do 2.5 unless we convert it either into a radical, using one of our radical properties, or if it simplifies like it did here, 6 over 3 becoming a 2. So let's look at this problem. I can rewrite this as 9 square root of 9 to the 5th power. Now, at this point, I can use any of the options from last time as well as any of the properties from today. One of the things that I could do, for example, is the 5th power means it's just that number written 5 times. Okay, now let me showcase kind of 2 ways we can go from here. One way we could go would be to break this up. This becomes the square root of 9 times 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 the square root of 9. Right, we could break it up into 5 individual radicals. And we all know what the square root of 9 is. It's 3. So each of these becomes 3's. And then 3 times 3 times 3 times 3 times 3 is 3 to the 5th. That's an acceptable answer. Or you could actually multiply that number out and get 243, which is the other answer. That's one way of doing it. Alternatively, we could write this as the square root of each 3 breaks down into 3 times 3 times 3 times 3 times 3 times 3. So this 9 becomes 3 times 3, 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 and the last 9 becomes 3 times 3, which means we end up with a total of the square root of 3, and we have 10 3's. We could then rewrite that as 3 to the 10 over 2. And we know 10 over 2 is 5, so this becomes 3 to the 5th, which is one acceptable answer. Or, of course, we could multiply it out. So these are just various ways we could go about trying to simplify this same problem, and they all use properties to do so. There's no magic tricks. There's no fanciness to it. It's just using properties that are clearly and well defined. And that's a necessary thing. Now, before we go any farther, it is important to note that if you have it in a fraction, this is a little bit weird, because you have to make sure it's going to cancel with the fraction. So if I wrote, for example, 4 over the 7th root of a squared, the only way to get my a to cancel with the 7th root is to make sure my a has a power of 7. So how do I do that? Well, to make this work, one of the ways to do this, I have to multiply by something. Now we talked about how to multiply to get rid of a square root, we just multiply by the same square root. Well, in this case, we're going to multiply by a similar concept. Now, we're going to multiply by the 7th root. And because we want to multiply on the bottom, we need to multiply on top. But we need to multiply so that this number becomes a 7. It's currently a 2. I need a total of 7 of them. I only have 2 of them. To make it a total of 7, I need to put 5 more into play. Because when I multiply these two together, a squared 7th power times a to the 5th 7th root would become 7th root. Because remember, when we have 2 radicals being multiplied, we just merge the 2 together as long as they have the same power. This becomes a squared times a to the 5th, which is, of course, the 7th root of a to the 7th. And the 7 and the 7 would cancel, leaving just a behind. So notice how my radical has disappeared. But I have to do it in such a way that makes my root match the power. So I had a power of 2. I need a power of 7, so I add 5 more. and I can't do it on just the bottom, so I make sure to do it on the top as well. This piece is the important one. It decides everything in the problem, and you have to choose it correctly. So notice how we chose it. We chose it by noting what the power was, a 7, noting what the current power was, a 2, and then matching the radical and then gaining to the appropriate power. So this was a squared. We put a to the 5th to get a total of a to the 7th, allowing us to cancel, leaving us just a behind. On top, we have the 4th root of, the 4 times the 7th root of a to the 5th. A to the 5th cannot cancel with a 7th root because they're not the same power. Nor if I wrote this out would it make it any better, which means that on top it just stays the same, which is actually pretty common. There's a 4 on top, there's an a on bottom. I cannot cancel those two. I cannot cancel in the radical because they're not both in radicals. I can only cancel in radical if they're both in radicals. And so this is as simplified as this function gets. If I did one more of these, for example, let's see, I did the cube root of 2 over the cube root of 25. What I can do, first of all, is I can rewrite. The cube root of 2 stays the cube root of 2. The cube root of 25 can be the same as the cube root of 5 squared. Remember, 25 is the same as 5 squared. So notice I already have 2 5s. I need a total of 3 to make this work. So I choose the specific fraction, match radicals, so cube root stays a cube root. I need to get a total of 3 of these. I already have 2, so I put in 1 more. Because I put it on bottom, I have to also put it on top. And now I can actually multiply this through. Now on bottom, I would end up with, let me change colors here, the cube root. 5 squared times 5 would be 5 to the 3rd. Note that here I'm using a property from 2 times ago, where if I have 2 radicals being multiplied, I just put the 2 radicals in each other. Notice the radical doesn't change, it's still the cube root, just the powers change. And on top we'd have the cube root of 2 times the cube root of 5. Now the cube root of 2 and the cube root of 5 I could merge together, becoming the cube root of 10. Cube root of 10 does not simplify. On bottom, the cube and the cube root can cancel, leaving a 5 on bottom. The bottom is as simplified as it gets. There's no radicals. On top, there is nothing to simplify the cube root of 10, because this breaks down into 2 and 5, neither of which shrinks. So this is an acceptable answer. This is how you rationalize these rational expressions. You have to make sure that you end up canceling to make this function work. Now, speaking of rationalizing, let's look at topic number 2. Topic number 2 deals specifically with problems like this. Get a good example here. Yes, there we go. 4 over 1 plus the square root of 5. If you come across a problem which contains both either addition or subtraction inside a fraction, specifically in the denominator, this is what really matters. It has to be in the denominator. This is where the problems can be. It's only if it's in the denominator that we do this step. So, only apply if denominator contains a plus a radical or a minus a radical. That's the only possibility. Or I guess you could do it if there were like double radicals. But again, it's only in the denominator that we do this. If it's in the numerator, we don't care. Okay? All right. Let's take a look at this problem. How do we fix this? Well, many of you guys may already remember, but to do so, we need to multiply by something called the conjugate. And to write a conjugate, we say if you have the expression a plus the root of n, then the conjugate equals a minus the root of n. And this works both ways. So if it's a minus the root of n, we'd write a plus the root of n. And so in this case, the conjugate we're going to use is the conjugate of the 1 plus the square root of 5. That conjugate would be 1 minus the square root of 5. And because we're doing it as a fraction, we have to do it on both top and bottom. Because remember, in mathematics, this statement cannot change in value. We are multiplying by a fraction that reduces down to 1, meaning we are not changing this value at all. We are just rewriting it in a different way. So note again where this conjugate comes from. Okay? If we have 1 plus the square root of 5, we multiply by 1 minus the square root of 5. And we'll do another example here in a little bit where we change signs and do it a little bit different. You have to flip the sign of the radical. So, what does this look like? Well, on top we have 4 times 1 minus the square root of 5. On bottom we have 1 plus the square root of 5, 1 minus the square root of 5. And you have to simplify this. There's no way to get around this. You must simplify. Now, how are we going to simplify? You could FOIL, which is what we're going to have to do on the bottom, or you could distribute, which is what we're going to have to do on top. Distribute. There we go. And so on top, let's distribute. 4 times 1 is 4. 4 times the negative square root of 5 would be negative 4 square root of 5. On bottom, we'd have to FOIL this out, so we take 1 times 1, which is 1. 1 times negative square root of 5, which is 1 minus the square root of 5. Square root of 5 times 1, which would be a positive square root of 5. And then square root of 5 times negative square root of 5, which would be the negative square root of 5 squared. You know how we just FOIL that out using standard algebra techniques from Algebra 1. We can simplify this now. On top, we still have 4 minus 4 square root of 5. On bottom, 1 is just 1. Negative square root of 5 and positive square root of 5 are going to cancel, leaving me with 0, so we end up with minus 0. And square root of 5 squared, the square and the square root are going to cancel, leaving us with minus 5. And so 1 minus, these two become 0, so it's 0, minus the square root of 5 squared is just 5, which means we end with 4 minus 4 square root of 5 over negative 4. This is okay, but I would expect it to go farther. We should always simplify as far as we can. We can factor a 4 out of the top again to go with that negative 4 on bottom. The 4 and the negative 4 can cancel, leaving a negative 1. This is one acceptable answer, the negative coming from the bottom. Or we could have negative 1 plus square root of 5 if we distribute it. And so you'll notice that it took a fractional power and made it not a fractional power. We got rid of that 1 plus radical 5, which is the problem, right? The denominator cannot contain a radical. Notice the denominator in this case disappeared, which is perfect. Let's look at an alternative example now. What if I have 7 over 2 minus the square root of 3? Well, again, we have to specifically choose the conjugate. Now remember, we match conjugates with the denominator only. So in this case, we'd have 2 plus the square root of 3. And we have to match top to bottom, so this would become 2 plus the square root of 3 on top as well. And now we have to multiply this through. On top, we have 7, 2 plus the square root of 3. On bottom, we have 2 minus square root of 3 times 2 plus square root of 3. You'll notice if you do this correctly, that when you distribute on top and bottom, the bottom is going to force the radical to disappear because of how we're choosing the conjugate. On top, we end up with 14 plus 7 square root of 3. On bottom, 2 times 2 would be 4. 2 times the square root of 3 would be 2 square root of 3. Negative square root of 3 times 2 would be negative 2 square root of 3. And negative square root of 3 times positive square root of 3 would be negative square root of 3 squared. Again, using my properties to do this a little faster. On top, 14 plus 7 square root of 3. On bottom, 4 is a 4. Positive 2 square root of 3 minus 2 square root of 3. These two match, so they're going to cancel. This becomes plus a 0. which is good, because this means that part of the radical has disappeared. Notice we also have the negative square root of 3 squared. Negative square root of 3 squared is going to cancel the square root with the square, leaving us with minus 3. And the square root of 3 squared, we simplify. On bottom, we end up with a 1. On top, 14 plus 7 squared of 3. Notice how we know this has worked well is because of what happens here. Look at where we started this problem, and look where we're finishing this problem. We started with this problem child. We cannot have a square root in the denominator, so we use the conjugate of that square root to get rid of it, leaving us with just a number in the denominator. Notice the top still has a radical, but that's fine. We don't care. We only care if the denominator has a problem. So in this one, it simplifies to 14 plus 7 square root of 3, and that's the answer. If you were to type this statement into a calculator, it's exactly the same as that statement, which is how you know you've done this correctly. For example, let me pull up my calculator here. So here's my calculator. If I type in my original function, which remember my original function was, oops, kind of hard to see. My original function was 7 over 2 minus radical 3. So I type in 7 divided by the function 2 minus the square root of 3. Close parentheses. Make sure I typed in correctly. Yep, looks good. It tells us this decimal is 26.124. Now if I type in this, it should match. That's how we know we did the math right. So I type in 14 plus 7 square root of 3. And look at that. It's also 26.124. So we know it worked. That's pretty crazy. It's pretty incredible. So make sure you take the time to verify your solutions. I don't want to see a single wrong answer, and you can do it easily just by typing in the calculator and verifying that the results work. And just to showcase, this is that carrot cake. Sorry, this is your caret. It's spelled differently than carrot. In order to do powers, so for example, if I wanted to do a square root, let's say, I could use the button to do the square root of 3, which is 1.732. Or I could do 3 to the 1/2 power and get the same result. Well, that's not incredibly useful. Like, that obviously took more time to type in that square root. If I had to do something like the, let's say I wanted to do the 7th root of 2,641, right? I don't have a 7th root on my calculator here. There's no 7th root anywhere on this calculator. So how do I do that? Well, I type in the number 2641, I hit the caret key, so do a power, and that power is, the 2641 has a power of a 1, and then my root is a root of a 7. And so the 7th root of 2641 is also written as 2641 to the 1/7 power, which is 3.0819. So that's how you use your calculator to determine your solutions. Again, that's our last material before our quiz tomorrow. Our quiz will encompass order of operations, it'll encompass these rational expressions, it'll encompass radicals, and the today's material. So make sure you can do everything we've talked about so far. Otherwise, I want you to be ready for your quiz. Please make sure you are ready. That'll be it. That quiz should be posted around noon tomorrow. I'm looking forward to it. Remember, it will be due on Friday at noon, just like normal, and that'll be the only thing we have tomorrow. So make sure that gets into me as soon as possible so I can get those graded. Otherwise, that'll be it. Hope you guys have a good Tuesday, and I'll see you guys next time.